we present Social Snapshot, a system for temporally coupled social photography. By leveraging recent advances in computer vision and the ubiquity of consumer-level programmable cell phone cameras, we design a system for the active acquisition of time-varying spatial data. Taking pictures of important people, places, and activities is an integral part of our lives. Technology has brought photography to our everyday life with such compact phone cameras. This project attempts to enable 3D photography using such devices. Users come together to socialize and collaboratively take pictures. To demonstrate how the Social Snapshot system works, we will illustrate how an example dataset flows through the system's pipeline and is transformed from unstructured but temporally synchronized photographs into a set of locally consistent 3D models to be browsed by the user. First, participants acquire synchronized photographs of a scene. Each of them uses a smartphone to take overlapping pictures from different viewpoints. The cameras are synchronized using the smartphone's network facilities to ensure snapshots of the scene are taken at exactly the same time. Though the phones are connected in a peer-to-peer manner, in each acquisition session, one phone is designated as the master and is responsible for determining the beginning and end of each session, and thus, the number of photographs acquired by each participating camera. Features are then extracted from the set of acquired photographs. Currently, the Social Snapshot system makes use of the popular SIFT feature descriptor, which is known for its robustness. Each SIFT feature vector is interpreted as a point embedded in 128-dimensional space. This allows a very fast and fairly accurate putative matching of features across different images within the same time step as a nearest neighbor search in the high-dimensional embedding space. The pairwise putative correspondences between images are considered as the edges of a feature graph. Non-one-to-one putative correspondences are removed. The connected components of this graph represent the set of SIFT features posited to be aliases for the same world space position. Each connected component is given a unique global identifier. An iterative structure-from-motion procedure is then used to estimate the pose of each camera that participated in the acquisition process. For each time step, we estimate the pose of an initial pair of cameras, as well as the world space positions of their overlapping features. The remaining cameras are then added to the reconstruction, using the reconstructed features and the putative correspondences for pose estimation. Efficient computation of correspondences between arbitrary pairs of cameras is enabled by the use of global feature identifiers computed in the previous phase. Patch-based multi-view reconstruction is then applied to reconstruct dense 3D point clouds using reconstructed feature positions and camera pose information. A separate model is constructed for each camera using the pose and feature information from this camera and its k closest neighbors, as determined by valid feature correspondences. Each point in the dense reconstruction maintains an average color, a corresponding visibility map, and a corresponding pixel location in each photograph which contributed to the dense point model. Just like the dense point cloud, each mesh is created using information for the current camera as well as its k closest neighbors. The surface is constructed from the point cloud as the solution to a constrained optimization problem. The energy we minimize attempts to obtain a smooth result while simultaneously agreeing with the observations from the dense point cloud at a small number of constrained locations. Each vertex in the mesh is given a texture coordinate according to its neighboring points in the dense point cloud, and the final mesh is then smoothly textured using the original photograph as a texture map. The interactive model viewer constitutes the final stage of our pipeline. Globally, the system produces a set of models which may be inconsistent. Locally, however, the models are highly consistent, and the smoothly interpolating transition between adjacent models allows for a near seamless navigation experience by the user. The user is allowed to navigate the reconstructed dataset in both space and time, and the freedom of navigation is constrained only by the available data.